Hello everyone. Let me share my screen. We have the MLT Edge AI Lab, and let me talk about MLT Edge AI Lab. How it all came with this is like a few years ago, I think 2 years ago, we had like a group of engineers and researchers. They visited the hacker farm in Chiba, and this is like a small community there. Like they have their greenhouse, and they were looking for some kind of like machine learning solutions or some kind of technology to deploy on the greenhouse. And they had a suspended robot. So what we did was like we went there, we saw what are the problems faced by those farmers and faced by the actual people working there. And then we were trying to do some brainstorming around how we can apply machine learning and agri-tech to actual applications and help those members. So that was, I think, the first initiation where we thought like we need to start thinking about like how we can apply machine learning to actual devices and actual real life applications. So after that, we organized one hardware working session. So this was, I think, also last year, where we organized a hardware actual hands-on workshop with Robot Club. And it was more like a weekend activity. On Saturday, we gathered for around like 3 to 4 hours. We had around 5 teams, and each team we provided all the hardware like Arduino, Raspberry Pi. Some members got their own hardware, and it was more like ideathon come like hackathon kind of thing, where like they had to create some application within that small time. And what any application is fine. So it was more like a free open lab kind of environment. And surprisingly, we got almost like 5 applications, like different applications within that small time. So that was something which also motivated us. Okay, this is really nice. And given a right environment, I think we could expand this into a big community. So uh, after that, we also participated in one of the SciNet competitions last year, where MLT got a third prize in the competition. The aim there was to develop a object detection system, and for the autonomous driving vehicles. And what we did was like for the competition, it was just a submission, but we went a step further there. Like after the competition, we deployed the actual model on Jetson Nano. So one of our members, Ben, he created this 3D printed this Jetson Nano case, and we deployed this Jetson Nano on bicycle. I think this is Naveen's bicycle. So we fitted all the camera and all the other stuff on the bicycle, and then did some real testing on actual data. So it was quite exciting when we see like these are the physical activities. So when it comes to Edge AI Lab, we realized like physical activity is really very important to have some kind of sessions. So, but then I think after this session, we had the COVID year, and for a long time we were not able to have this physical sessions. So we are thinking how we can come up with some exciting series in even within the COVID period. So with that, now Naveen and I were discussing like about like this topic, and we thought like we should have this kind of like AI application series, wherein like since we cannot meet offline, we do it online. And what we do is like um, we want to share like, I mean, whatever applications we can build at home, and then share it to the community, so and motivate each other so that they can build their applications by themselves. So we came up with this format of series like in terms of 4 sessions, and the main goal of this series is to allow to help all of the community, and even help ourselves to think of some application, think of it to develop it from scratch, and start making that application directly going it hands-on from right from working from home. So the aim is to like right from start, we will see like we want to build some application, we want to document it, share it to the members, and then with sharing, it also comes like we learn more. So that way we want to help everyone and even help ourselves to create some exciting applications around Edge AI application by the end of the series. So overall, this series will be divided into 4 sessions, wherein like today's session is the first session where we will give a general overview of Edge AI applications. And then the next session, next 2 sessions will be mainly focused on motion application and audio-based application, where Naveen will dive deeply into how to use motion data, how to use audio data, and build some cool applications around that. And the last session, we are looking forward to do some wrap-up session, wherein like we are looking forward to teams from this particular session. Like during this series, we are continuously encouraging like we should form some small teams and try to think some application, so that by the end of this series we can present those applications. We like, I mean, our main focus will be to guide you, to help you build your own application. So that is the reason why we will show you some demos, show you how it is done. If you have any difficulties or any kind of challenges, then that is where we will pitch in and help you around those topics. So for all the discussions and everything, we'll use Slack. We have the Machine Learning Tokyo Slack, and we have a channel, Edge AI Lab. So please join this Edge AI Lab channel on MLT Slack, so we can do more discussions and continue discussions over this entire series in that channel. So with that being said, let me jump into today's agenda. So yeah, so our this series is organized by 2 members, Naveen and me. So let me hand over to Naveen. Naveen, can you please introduce yourself?
Yeah, thank you, Raj. So hi, everyone. I'm Naveen Kumar, and I work at RIKEN, one of the largest research organizations here in Japan. And mostly I work with the DNA protein data or genomic data sets, but I got interested in AGI 2 years ago, and I created so many projects at Hackstar.io. So you can see in this picture, so these are all projects related to the AGI, mostly running on the small microcontroller, and they have a very diverse kind of nature. And in my free time, I like watching movies or doing the nature photography and mostly working with the microcontroller. And you can find me anytime with all my updates at my Twitter handle, like at knaveen. So yeah, so maybe Yoovraj can
Yeah.
introduce yourself.
Yeah, thanks, Naveen. Whenever I see your this page, I really get excited because there are so many cool projects here, and like sometimes I also try to see understand this, and I think the documentation and everything is really good. So anyone can easily learn from that particular project. So yeah, thanks, Naveen. So I myself, I'm Yoovraj, and basically my background was in electronics engineering, but after that I am right now working as a software engineer and also a team manager. I'm a co-founder of MLT and leading the Edge AI Lab. So with Edge AI Lab, I think the first motivation I remember to my first motivation to join to come into AGI and machine learning and robotics was this project which you see in the GIF. I remember this was all the start of like where I joined Machine Learning Tokyo and together with Susanna, and this was a simple robot. Like I thought like I don't want to make my tea, and dipping is like a continuous activity which I want to automate it. So I just use simple Arduino and basic motors with feedback, and then like recorded some particular actions, and then the actions got replayed again and again. So that was like a simple model, just copying and replaying things. But that was where like a lot of people told, okay, this is nice. So maybe during that hackathon, we had one a small humanoid where you see in the second picture here, like this is an open source project called as Plen. And they have like the basically, if you want to make a humanoid walk, you had to program a lot of steps. You had to write a lot of code to make each joint move with some particular angles. So I thought like, why don't I scale this part, like where I just instead of recording this individual motors. I record all the signals from all the motors of this humanoid and then replay them. So that was my project, which is like still ongoing. Like I had to shut down a few years ago due to some busy work, but I'm thinking like now reopening this project along with this series so that I can learn together with Naveen and the entire community and try to make it better than the previous version. And then the other project which I am quite interested in is it like robotics for kid. Like I love making small cars and robotic cars for kids and playing with them, especially around with Raspberry Pi and Scratch. So that's my basic like background and interest and motivation. So with that, let's jump into why we are talking about Edge AI and why Edge AI is so important. Is There are many reasons actually. So if you see right now, uh, if you see like the general approach, you have data on the edge, data on the devices. And say suppose you want to make some machine learning model which want to utilize this data, you train the model on cloud and then you deploy it as an API which is on the cloud. So you have data on edge and compute on cloud, and then how do you connect these two is via some kind of like channel. It could be like internet or any kind of like internet or some kind of protocol. So there is always involved, there is always some kind of latency, some kind of like security aspect, user privacy aspect, a lot of extra cost things. So this this is where I think the thought came in, like why don't the compute and the data be close to each other? And that is where the edge AI applications or deploying on edge comes into picture. We have the data on the edge and the compute also on the edge, and then this helps to solve a lot of problems. Like we have the offline processing, which is like an independent system. Then we have the user privacy and security. So since the data is already on edge, you don't send it anywhere, so you can process the data at the source itself. Then you have low power systems, low cost systems, low power systems. When you say it's like the edge devices, they are generally like literally low power, ranging from some few milliwatts to few watts, like 10 watts or something like that. And the important feature is portability. So these are the some of the important factors which makes edge AI so important. And I just put one graph here. Like you see, as more and more devices and more people are getting connected by so many IoT devices, and there is so much of data exchange between these IoT devices. So you cannot, and there is a need for machine learning on for each of those devices because there is so much of variety of data. So there is a need to have better compute together with the data. And you see, like you have so many wristwear, eyewear, or these kind of like wearable devices coming in, and year by year they are increasing. So we need to have something which is near to the data, where we can easily deploy and make sense of the data there itself. So with that being said, the importance of edge AI, I would like to just briefly touch on what are the general blocks of edge AI pipeline. This is like a very generalized version which we work together, and depending upon the each use case, this might differ. So um, generally it comes with like data collection and storage as the main part on edge, and then you have the cloud pipeline wherein like you have processing, model tracing, model quantization, pre-processing, and then again you go back to the edge to do on-device deployment and inference. So with that, let me hand over to Naveen, who will explain more about like the use cases and the details about the pipeline.
Yeah, thank you, Yoovraj. So in the upcoming sessions and in these sessions, we will be mostly talking about the AGI related to the microcontrollers. And these are the some example use cases for AGI. So I have divided the domain into the three parts mostly. So one first is the inertial sensors that are like accelerometer or gyroscope or magnetometer, or it could be environmental sensors. That could be the gas sensor or temperature reading or barometer reading. So usually in industry, they use this kind of sensor for the predictive maintenance, to knowing like what is the, I mean, if some repair is needed for some machinery in factories, so they can use this kind of sensor to know beforehand. And also they are used for the body monitoring. So use cases are maybe in medical use cases or activity recognition, and it could be sports activity. And in audio analytics, we can have the audio scene classification. So for example, if you have if you know about what kind of audio scene is, then you can do some kind of action, like you can do the noise reduction. And for audio event detection, it is just like breaking the glasses or some audio event happened, so you can take some action. Or keyword recognition, like the hey Alexa or hey Google, this kind of things are keyword recognition. So those are actually done on the very low powered microcontroller without need of any cloud. And for the image analytics, we can do the surveillance and monitoring. Those are very, useful use cases. And these are used in the autonomous vehicle where we use the LiDAR sensor or camera to detect, for the autonomous behavior of the vehicles. And for the expression analysis to improve shopping or advertisement or driving. So just looking at the facial expression of the user, and then you can decide the shopping experiences. So this kind of all small sensors are installed in the shopping malls, and actually in near future you will find them frequently. Next slide, please. Yeah. So we are going to talk about the type of edge hardware we can use for this kind of purpose. So you can see in this picture, these all hardware actually I own, and I try to push all kind of models for the experiment on these hardwares. Like almost 2 years I spent on these all hardwares to making some kind of inferencing. But these all hardware has different capacity and different capability. So there could be the bare metal. So bare metal means you don't have any OS in hardware. So they are just bare metal microcontroller, and then you use just C++ or C firmware, and you can just use that. Or it could be the RTO based. So RTOS based means real-time operating system. So if you use RTOS, then you can have a multi-threaded application on the microcontroller. Or you can use the embedded Linux. So for example, on Jetson Nano or in the Raspberry Pi, you can use those things. But there are also very small Linux devices you can find everywhere, like in an oven or in your refrigerator. They are there actually. So, and we have the ML accelerator. So ML accelerator could be like Google Coral or the Intel devices, that is the neural compute engine. So those are actually works with some kind of host computers to accelerate the CNN, mostly CNN models. And the mileage varies from 16 megahertz to like around 1.5 gigahertz. So these are the clock speed of the microcontroller or microprocessor. And the wattage can be varied from 100 milliwatt to the 10 watt. And the RAM, that is the memory of the edge devices, that is also can be from 2 kilobyte in the Arduino Uno, or it could be the 8 gigabyte in the Raspberry Pi or similar boards. Next slide, please. So in the next slides, I will be mostly talking about the hardware-based, edge-based devices and the deployment on that. So first stage of any machine learning pipeline is the data collection, and that also applies to the edge AI. But this part is also very interesting and also challenging, because if you don't have a right kind of data, then your further pipeline is not going to work. So for the data collection and storage, there are many kind of sensor interfaces. So if you have a sensor, we have a different kind of sensor like accelerometer or camera or audio devices like microphone. You can have a GPS, or you can have an ambient light system. So they are actually different kind of systems. So you have to interface those using different kind of interfaces. So we have a I2C or SPI, PDM, UART, analog. So not all microcontrollers support these kind of interfaces. So it depends like what kind of data you are going to collect. So you have to actually choose those kind of development board to work with. And if you are working on the data collection, then you must know what is the sampling rate and how you are going to use those sampling rate into your model. So for example, for accelerometer data, you can actually do the sampling on 25 hertz. That is like 40 millisecond of data in per second. I mean, this is the just kind of rate. Or if it is the audio data, so it could be like 8 kilohertz or 16 kilohertz data. And once you, I mean, collected the data, but before there could be some kind of pre-processing. Like suppose if you want to collect data from the factory calibrated sensor, but it's not going to work with your use cases. So for that, you have to do the sensor calibration. So sensor calibration is just you kind of calibrate your sensor to work with your environment, because not all sensor work, I mean, exactly same. So you just calibrate the sensor. And sensor fusion is maybe your model is going to trained on the different kind of sensor at the same time, like similar but different kind of. For example, you have the accelerometer and you are going to use uh, maybe accelerometer data only or gyroscope data together. Then you do some kind of sensor fusion. But you have to keep in your mind, when you do the sensor fusion, then you have to uh, keep the sampling rate the same. So sometimes you have to undersample one of the sensor, or you oversample another sensor to keep it at the same sampling rate. And we can have a time series data or non-time series data. So most of the accelerometer data or audio data are time series data. And for example, camera snapshot, those are actually non-time series data. But if you are trying to find some kind of event in a video, that could be a time series. And in this figure, actually, I'm trying to collect the particular matter. So particular matter is just the air quality indexing thing. So you find some kind of dust in your indoor house or maybe some office. And environmental sensor could be the temperature, or gas sensor could be the CO2. So this device, actually, I have connected two of the sensor, which is actually connected over the I2C interface, and they are actually storing the data into this device. So this device is the bioterminal with the display, and you can, the data is actually being collected on the SD card and also being sent to the cloud. And here, actually, we can divide the data collection strategy into three part. Like it could be the completely offline. So you just use the micro SD card in your development board, or you can use the flash memory. So flash memory is actually some kind of embedded memory in your development board with the microcontroller. So you can directly use that. Or you could have a SPI memory, that is, you can actually extend your flash memory with the external chips. So these are actually completely offline storage. Or you can have an online storage, so you can directly use the cloud. So you just sample the data on your microcontroller, and using some protocol, communication protocol, you send the data to the cloud. Or you can use some local gateway, for example, Raspberry Pi. So you don't want to send your data to the cloud, then you can store in some other Linux machine. Or you can use the hybrid approach. So hybrid approach is you store data locally, and then later you upload to the cloud when internet is accessible. Or you do some kind of batch update. So suppose you just collect the data for 10 minutes or something, and then uh, send it to the cloud, uh, maybe some interval. And there are some protocol actually for microcontroller based data collection. So because, I mean, the Wi-Fi and other protocol like HTTP, HTTPS, those are very, I mean, expensive protocol, because they have a large firmware size. If you try to burn into your microcontroller, then your flash size, it needs like large flash size. So we use actually very low bandwidth communication protocol. So those are actually LoRaWAN or LTM, NB-IoT. So LTM and NB-IoT is your cellular based protocol. So it uses your mobile network. And MQTT is based on the Wi-Fi, but it will use very low lightweight protocol. And BLE is the very lightweight Bluetooth protocol. So you can actually connect your phone also to your microcontroller over the BLE, and you can store the data to your phone. And later you can share with your, I mean, some cloud or somewhere. And here in this picture, this video actually, I'm trying to collect data from a thermal image over I2C. And this image is actually captured in real time and saved into a SD card, which is attached to this device bioterminal. And the data is actually the far infrared thermal sensor. So those are just the thermal reading, but those are converted into some kind of image. So your model can actually understand the image. So these are actually the example of the real-time sensor data. So actually this example I have captured from the Arduino NanoBLE board in real time. And you can, so I am showing you this image because you can have better understanding of the data you are going to capture. So in the first image, so we are capturing the accelerometer data. So accelerometer data actually has the 3 axis data. So it has the X, Y, Z axis, and you just collect the data, floating point data. And it has the sample rate, 119 hertz. And then for the microphone, so we usually use the PDM interface. There are actually many interfaces to connect microphone to the microcontroller. So PDM is actually pulse density modulation. So it collects the analog data and convert it into the digital data at the sample rate of 16 kilohertz. And in this example, I'm just capturing the mono channel. So that is the single channel data. So this way, actually, you have some idea like what the data looks like if you visualize them. And this is just the number which model going to see actually. So before actually working on the model, we have to actually work on the data. So we collected the data in raw format, and we have to do some kind of processing, and then we have to extract the feature. So we usually use the digital signal processing for the pre-processing of the raw data. So there are some steps for doing this kind of processing, but not all processing steps are required for the raw data. It depends on what kind of sensor you are using. So it could be something different. So, but usually we do some kind of a scaling of the data to fit into some scale or some range, and we do some kind of filtering. So filtering could be you remove some kind of noise, maybe you remove the higher frequency, or maybe you remove the low frequency, or maybe you just keep something between. So that we call the band filtering. So, and also we do the normalization of the data. So normalization is just you are changing the value of the data to fit within some ranges. And for the feature extraction, there are other many methods. So for accelerometer data, for example, we usually do the flatten. So flatten is actually just some statistical value we collect from the data. It could be the average, or it could be the minimum maximum value, or RMS, standard deviation, skewness, or kurtosis. It could be anything. And you have to actually later choose which feature actually fit, I mean, represent your data better. So that are like more research things you have to do iteratively. And there are another method that is more suitable for the accelerometer, so that spectral analysis. So in spectral analysis, we usually use the Fourier transform. So accelerometer data is actually analog data, and we convert that data into the digital format. And so those data is just a number, and we actually uh, convert those raw data into using the spectral analysis, and we actually convert that into the power spectrum data. And those data is actually really useful for training. And for the audio data, we usually use some kind of standard algorithm. Those are the male frequency spectral coefficients, or we use male filter bank energy, or it could be spectrogram audio for the audio data. In this image, actually, you can see the top image is raw audio data. So you cannot actually distinguish. If I show you all the raw audio data, you cannot visually distinguish them. But when you apply the digital signal processing and create for example, a spectrogram, then you can actually see the data. And the different image will have some kind of different specific feature or pattern, which is recognizable visually also, and that is very good for the model training. So for the model building, we have to think about many constraints and many, I mean, limitations, because it's not like we are going to train the model on the GPU and inferencing on the big machines. It's like you train, I mean, you can train the model on the GPU, but ultimately you have to run the model on the very, I mean, bare metal or RTOS based microcontroller. So there are limitations. So for the model building, usually we use TensorFlow Lite for microcontroller. So this is actually very specific library, which is available for Arduino, or maybe you can use directly in the C++. And there are actually limited support for the TensorFlow operations. So you cannot use all the operations you used to use in big model creation. And not all model architecture are possible because not all TensorFlow operations are supported. So these 2 points are actually linked. And the model must be small enough to fit within the target device memory, because sometimes you train the model and you compile the model, but it will not fit into the flash memory or RAM of the target device. Um, so you have to keep in your mind. So when you iterate the model building process, so you have to actually go through many times for this model building process. So suppose first time you create a model, but when you burn into the target device, so it will give some error like there is not enough memory is available for this particular model. And there are also the trade-off between the model size, complexity, and the workload and duty cycle. So workload duty cycle is the performance thing, and model size and complexity is the like how deep your model if you're using the neural network, or what is the size of the network. So somehow you have to find some sweet spot. So its model size is also moderate and it's also performing very good. So that also we have to keep in our mind while creating the model. And usually we train the model for 1 or 2 iterations to check model size and supported operations. So sometimes there are tools available. So when you convert the model, so in the next step, when we convert to the model using the TensorFlow Lite converter, so that will actually give you some kind of hints, like this operation is not supported. And finally, everything is okay. Then we convert the model into a C byte array. So C byte array is just the kind of variable. So you convert the model into some array, and then that array will be stored into the target device. So after the creating the model, we have to actually do the training. So training process is exactly the same as you do on the big computer or maybe in cloud or on your local PC. So those are exactly the same. So after the training, so we have to do quantization, because when you train the model, so the final model size will be big. So we can actually convert the model into the very small size using the quantization process, because most of the low-end edge devices has limited floating point support. So not all the edge devices support the floating point. Even they support, so those are very limited, like that could be 16-bit or 32-bit. So we use the quantization here. And mostly we use the post-training quantization, but you can also use the quantization aware training. So if you do the post-training quantization, so it reduces the model size. That is one first point. And it also actually improves the CPU and hardware acceleration latency. So it will run actually faster after the quantization. And most of the time there is a little degradation in the model accuracy, but it's not the case every time. Sometimes you will see the floating time model is doing better job. And in that case, we use the floating point model if the target device allows. And usually the 8-bit quantization approximate floating point value using this formula. So this is actually very simple formula. Like you just convert the real value. Real value is actually the floating point values, and you do some kind of a scaling. So in this image, actually, you can just visualize like how it is being done. So in the lower image is actually the floating point value from the some negative big number to some positive big number. And you actually just shrink the model, I mean the range between the minus 127 to plus 127. So minus 127 to plus 127 is actually the 8-bit range of the integers. So next, I will talk about the on-device deployment and the inferencing. So on-device deployment, we actually, before doing the deployment, there are some steps we can use if our target microcontroller allows. So if suppose if you are using some ARM Cortex M device, so there are some CMSIS DSP and CMSIS NN libraries are available. So we can compile using those library, and those library contains the pre-compiled some kind of assembly, uh, maybe very fine-tuned neural network. So it will convert the existing neural network into those implementation, and they will run really faster. And then after doing optimization, if needed, we actually compile the firmware. So suppose if you are using the Arduino IDE, so there are standard steps in the Arduino. You just click one of the button here in the Arduino IDE, and it will just compile your model, or it will give you some error message if some uh, syntax error or there are something happening. Also, after the compiling the firmware, you usually burn the compiled firmware image to the target device. So burning means we are not going to put our device into the oven, of course. So we actually just upload the firmware image to the target device. So if we are using the Arduino IDE, you just click one of the button in the menu bar, and it will just flash the device. And during the flashing, it will also give you some kind of hint like it is not getting fit into the flash memory, or some kind of like overflow of the memory. So you can see in the image here. So this is the memory map of the microcontroller, which is on the Arduino NanoBLE sense. That is the Nordic microcontroller. So this is a specific memory map, but this is some kind of generic. I mean, some things are not same with other microcontroller, but most things actually similar with the other microcontroller. So we have to always think about only the code area and the SRAM area. So SRAM is the coupled memory, which is directly coupled with the microcontroller, and there are RAM area, which is just the memory area. And if you are just, I mean, wondering where this firmware will be written, so there are some specific address in this flash memory. So in the code area, this firmware will be written using the Arduino IDE. And later when you boot up the development board, so those firmware will be loaded into the memory, and it will execute it from there, from the RAM. Let's talk a little bit about the microcontroller. So microcontroller are typically small and low powered, and they are specialized computer kind of, and they are tasked with the single program. So they will run only one program. And if you are using some kind of RTOS, that is real-time operating system, so you can kind of mimicking, like it's based on the time slicing of the microcontroller. So they can run multiple. And microcontroller actually bridges the physical world to the digital world. So physical world is like your sensors, and those are actually analog, and you actually convert those into the digital using microcontroller. Actually understand only digital things. They don't understand uh, analog signals. So they are just the electronic interfaces. And by advent of modern tools chains, now it is very easy to program this microcontroller. So in this image, this is the Arduino Uno R3. This is a very basic microcontroller having only 2 KB of RAM. And so in this image, the whole thing is actually a development board. So there has many things like interfacing the sensors and like programming the microcontroller. But the microcontroller is only the red rectangular thing. And you can actually plug it out and move into in some other your setup. So everything actually works only on the microcontroller. You don't need the whole development board, but we use the development board for the developing the firmware and testing those things. But it's up to you. You can actually move those things into some product, and that's why we call it the embedded electronics. So we talk a little bit about Arduino. So Arduino actually is a kind of ecosystem. So it is also a hardware, it is also a software, it is also a community. So Arduino was born in 2005 as a tool for the student with the electronics and program without any electronics and programming background. And it is open source both as a hardware and both as a software. So you can take the schematic of Arduino and you can create your own Arduino board. It's okay. And they have actually really large user community. So if you have some problem issue, just go to their forums and you will get the answer quickly. And it's actually cross-platform ID, so you can install it in most of the operating systems like Mac OS or Windows or Linux. And they have actually many libraries available for common tasks. So most of the time, if you are using some of the sensor, so 90% chances are you will find a library in their code base. Otherwise, you have to come up with your own library if it is new sensor or something. So this is the Arduino NanoBLE sense board, which we'll be going to use in our upcoming sessions where we will be doing some kind of hands-on. So we actually chosen this board because it has a like many sensors in one single microcontroller board. So you don't have to actually interface external sensor because they are already on board. And they are actually inertial sensors like accelerometer, gyroscope, magnetometer, or environmental sensor, that is humidity or pressure sensor or temperature sensor, or you can have the proximity light sensor, and it has an onboard microphone. So you can actually record your voice. And it's, I mean, so many sensors, so it is a reasonable price, so $30 USD dollar or around 4,000 Japanese yen. And it has a moderate clock speed that is 64 megahertz, and it has a 1 megabyte of flash memory that is enough for like any program with model and other things for AGI actually purpose. And the memory is actually 256 KB. That is enough for voice-based application and IME, I mean motion-based application. And for to some extent, you can also do some kind of vision-based AGI application. That is also possible on this board. Before, I mean, going to the next session, we have to actually create a development environment setup. So I'm just giving us some small demo of how you can install the Arduino. So you have to go to the Arduino, just search on the Google, and there in menu, you have to go to the download page, and you can find many different cross-platform ID, and just go to the download. And once you download it, since I am using the Mac OS, so just move into the application folder. But if you're using other operating system, then you just follow the manual there. And once it is installed, then you just open the ID. And once it is opened, then actually you can find one template code. And we are going to actually test the NanoBLE. So first, before that, actually, we have to install the NanoBLE Arduino core. So every microcontroller, you have to install the core for that in the Arduino IDE, because Arduino IDE supports many development boards. So I have installed one Arduino NanoBLE core, and then we will try to test the development board. So here I have just chosen the board, which is the NanoBLE, and then we will use the examples, one of the blink examples in the menu. And actually there are many pre-made examples you can find to just test the board. You can just go in the different sections of the menu, and then you can find basic examples. So here actually I'm going to use one of the simplest example. So that is the blinking the LED, the onboard LED. So you just choose that example, and then it just blink the LED on the NanoBLE every second. So very simple code. You can actually, it's just 4 lines or 5 lines of code. And then you just compile using one of the button at the top menu. And once the compilation is done, then you will see like how much memory it's going to use on the target device. And once the compilation is done, then you click another menu upload button, and it will be flashed into the target device. And in this GIF, actually you can see it is blinking. So in this demo, actually I'm going to show you one of my project at Hexter.io. So in this project, actually I made one activity or maybe posture detection device. So it will tell you like your posture is good or bad. So I have actually wearing a development board on my hand. And in the first video, I will be doing the data collection. In the second video, I will be doing the inferencing. So you can watch this.
Hi guys, I am going to give a live demonstration of the data capture. So this time I am going to collect the data for walking. So this is the DK which is connected to the Adafruit shield, and here is the BLE peripheral which is connected to the accelerometer, and both are getting power from the power bank which is inside my pocket. So first start the DK. This is the central device and the peripheral is connected and data is streaming. So just click on the walking, and then I have started walking, and you can see, so data is streaming. So you can see this in the graph, and the data is actually getting captured into the buffer. Thanks for watching. Hi guys, I'm going to give the demonstration of inferencing. You can see the BLE peripheral device is connected to an accelerometer, and it is sending 2 seconds of the data to the BLE central device, that is NRF5340, and I position myself in good posture, so the device should say I'm in good posture. And if I tilt a bit in the bad posture, then it should change the bad. And if I start walking, then it should say walking, and if I running, then it says running. Thanks for watching.
So these were the example actually.
Hi guys, I am going to give live.
You can stop. Okay, thank you.
Yes, sorry.
Yeah, so these are the example actually. So later in next session, we will be making similar kind of applications. So Yoovraj, maybe you can continue from here. Thank you.
Yeah. So yeah, with that, let me close today's session. I think we already went well over the time, and sorry for that. And thank you very much, everyone, for staying over the time. That's it for today. Our next session will be next week on Sunday, and we'll try to plan it in much better fashion. Thank you, everyone. Thank you, Naveen, and thank you, everyone.
Yeah, thanks everyone.
Thank you. Have a nice weekend. Bye-bye.
Have a nice weekend.